Okay. This is problem 5.138A from the final review.
All right. So this problem says suppose x has a uniform distribution on the interval from a to b, and then we want to use the properties of the moment generating function to derive the moment generating function of y, which equals cx plus d. So I think in your homework you found the moment generating function for a uniform random variable. So I guess I could repeat that process just to do it right. So let's do that, I guess, first. So first we'll find the moment generating function of a uniform random variable, and then we'll find the moment generating function of this new random variable that is some linear combination of this uniform random variable. So for the moment generating function of x, which you guys should have done in your homework, we're gonna have, right, if it's uniform from a to b, that means the probability density function, right, of that random variable is going to equal 1 over b minus a, and that's from when x is between a and b, and it's going to be 0 otherwise. So we want to find first the moment generating function of x in terms of t, and this is the expected value. This is the expected value of e to the tx. So this is going to be, we're integrating now from negative infinity to infinity of e to the t, now little x, times f of x dx. And then this is going to equal, in our particular case, the integral from a to b of e to the tx times 1 over b minus a dx. And now this is going to be a constant. We're integrating with respect to x, so we can pull that out of the integral. So this is 1 over b minus a times the integral from a to b of e to the tx dx. Now this integral is going to be what? So we have 1 over b minus a, and then we want to have this e to the tx term, right? We know when we take the derivative of this, it's going to be the same thing, but then by the chain rule, we're taking the derivative with respect to x, we have to multiply by the derivative of this inside, so that's going to make this t come down. But we don't have a t here, so to cancel that out, we need this 1 over t when we're integrating. So now we know that when we take the derivative of this, we get back to e to the tx. And then this is going to be evaluated from a to b. So now again, we evaluate this by first plugging in the top number. So we have e to the tb minus plugging in the bottom number, so e to the ta. So the moment generating function for x, for this uniform random variable, is going to be, if we combine these, e to the tb minus e to the ta divided by t times b minus a. So again, this is the moment generating function of x. So now we want to use the properties to find the moment generating function for this new random variable, right? So now we're defining a new random variable, that is y is going to equal to I think, what is it, c excuse me, cx plus d. So now we're going to use, we want to find this moment generating function of y in terms of t. So this is the expected value of e to the ty, but then y is cx plus d. So this is the expected value of e to the t times cx plus d. Then we can distribute this t. So this is the expected value of e to the t cx plus TD. And now this is going to equal the expected value. So when I'm, expected value of e to the TCX times e to the TD. So remember, when I'm multiplying these two, they have the same base. I add the exponents. So I can go the other way around too, right? If I'm taking e to this power of something plus something else, I can set that equal to e to the power of the first thing times e to the power of the second thing. And now notice that I'm taking this expected value in terms of x. And like we did up here, when we took the expected value, this becomes an integral in terms of x. So I can pull anything that doesn't have x's in it outside of that. So in this case, this is going to become an integral. So this doesn't have any x's in it. It can come outside of the integral. And then I have the expected value of what's left. So this is going to be equal to e to the TD times the expected value of e to the TCX. And in general, if I have any constant inside of an expected value, I can always pull that out. So now what is this? This is very similar to what it says for my moment generating function of x, except for instead of a t here, I have a tc. So what is this really? This is the moment generating function of x evaluated at tc now. See, I can put little parentheses around here. And then I have times e to the td. And this is going to be equal to my moment generating function of y. And that is my answer. Oh, and also thank you to my assistant.
Yes, me.
Yes,
me.
she was
And
very
Frog.
helpful. And
Frog.
yeah.
Let me have Frog speak.
No, I don't think we have time for that.
Please.
Okay, I guess Frog is gonna speak now.
Okay. Here goes Frog.
Okay. He's taking his sweet time. Okay, that's good. Alright, goodbye.